Greetings, differential equation scholars, and welcome back to our video series on the Laplace transform. In this video here, we begin a sequence on section 7.2 dealing with the inverse Laplace transform. Suppose that we know that a function little f of t has a Laplace transform that is capital F of s. If that is the case, we can say that the inverse Laplace transform of the function capital F of s is the function little f of t. And we'll write this notation with the -1 power of the Laplace transform symbol to indicate that we are talking about an inverse Laplace transform. So inverse Laplace transforms reverse the process, where Laplace transform takes a function of t and transforms it into a function of s. Inverse transforms do the reverse. They take functions of s and they return a value, a function that is a function of t. Let's take a look at a few preliminary examples of finding inverse Laplace transforms. We know from our work in section 7.1 that the Laplace transform of e to the 6t is going to be 1 over s minus 6 because of our rule for the transform of an exponential. Well, let's write that statement in a different way. If it's true to say that the Laplace transform transforms e to the 6t into 1 over s minus 6, then it's also correct to say that the inverse transform transforms 1 over s minus 6 into the function e to the 6t. E to the 6t would be said to be the inverse Laplace transform of 1 over s minus 6. As another example, consider the function 5 times t squared. We know from our work in section 7.1 that when we take the transform of a power of t, we get a power of s that is 1 higher than our power of t down in the denominator of the fraction. So that the transform of t squared is 2 factorial, or 2, divided by s cubed. So that means that the Laplace transform of 5t squared is 5 times 2 over s cubed, or 10 over s cubed. Well, let's take that statement and say it in a slightly different way. If it's true that the transform of 5t squared is the rational function 10 over s cubed, then it would be also true to say that the inverse transform of 10 over s cubed is the function 5t squared. Consider the next example. We know that if we transform cosine of 5t, the Laplace transform of the cosine of 5t is going to be s divided by s squared plus 25, according to our rule for the our rule for the Laplace transform for the cosine of kt. Well, if it's true that Laplace transforms cosine of 5t into this function of s, then it's also true that the inverse transform of s over s squared plus 25 would be the function cosine of 5t, since that's the function whose transform is s over s squared plus 25. So this is our basic idea of what we refer to as an inverse Laplace transform. Inverse Laplace transforms ask, what is the function of t that transforms into the function of s that I have? Let's take a look at several examples of finding inverse Laplace transforms. Suppose we wanted to find the inverse Laplace transform of 15 over s to the 5th. How would we begin? Well, we do remember the rule that says that if we start off with a power of t, then you can get a rational function that has the next highest power of s in the denominator. So since we have a fifth power of s here, that suggests that we investigate the transform of t to the fourth. What is the Laplace transform of t to the fourth? It's 4 factorial divided by s to the fifth. And 4 factorial is 24. So the Laplace transform of t to the fourth is 24 over s to the fifth. That has exactly the same overall form as the function that we are looking for here. It's not the same function, but it is fundamentally the same up to a constant multiple. So what will we do? We know that our answer is going to be some constant multiple of t to the fourth. How will we find out which constant multiple? Well, we need a constant multiple a that when we multiply it by the 24 that we know that we're going to get when we transform t to the fourth, we want alpha times 24 to be equal in the end to the 15 that we want in the numerator of this fraction. Well, that suggests that alpha should be 15 divided by 24, or more simply 5/8. So we want alpha to be 5/8. In other words, 5/8 times t to the fourth should be our function. Let's check that. If we transform 5/8 times t to the fourth, by linearity, that will be 5/8 times 24 over s to the fifth. Well, 24 times 5 is 120, which divided by 8 is 15. So 15 over s to the fifth. There you go. We have now found the function that transforms into 15 over s to the fifth. It's 5/8 times t to the fourth. So that's our inverse transform. We would say that the inverse transform of 15 over s to the fifth is 5/8 of t to the fourth. As a further example, let's take a look at finding the inverse Laplace transform for a sum of 3 terms. 5 over s minus 2 minus 2 over s plus 8 over s to the fourth. What if we're finding the inverse transform of the sum of those 3 terms? Well, we can use linearity here. Just as the Laplace transform is a linear transformation, the inverse Laplace transform is also linear. That means to find the inverse transform of the sum of these 3 pieces, I can find the inverse transforms of each of the 3 pieces separately and add those together. So what are the inverse transform of 5 over s minus 2, of negative 2 over s, and 8 over s to the fourth? Well, the first piece, 5 over s minus 2, we should recognize that immediately as coming from an exponential, specifically coming from e to the 2t. But it is by linearity, it is the transform of 5 times e to the 2t. So the inverse transform of 5 over s minus 2 is 5 times e to the 2t. What about our next piece? We have negative 2 over s. Well, that's negative 2 times 1 over s, and 1 over s is the transform of 1. So we recognize that the inverse transform of negative 2 over s is just the number negative 2. And how about our third term, 8 over s to the fourth? What function has this as a transform? Well, we once again remember that if we're going to achieve a power other than a first power of s down in the denominator, we need to start with the next lower power of t. And since this is a fourth power, that suggests that we start with t to the third power. But the transform of t to the third is 6 over s to the fourth, and we want 8 over s to the fourth. So we need another constant multiplier here. We need to have a multiplier in front of t cubed, so that we'll end up having 4/3 times 6 over s to the fourth. If we take that, we can see that 4 times 6 is 24 divided by 3 gives us the 8 that we're looking for. So our third piece is essentially a t to the third piece, but not just t to the third. It must be 4/3 of t to the third to get the constant 8 that we're looking for in the numerator here. So by putting those together then, by finding the inverse transforms of each of the three pieces and then adding them together, we have the inverse transform for the whole expression. It would be 5 times e to the 2t minus 2 plus 4/3 times t cubed. Here's an interesting example that is motivated by one of the examples in our last video. Suppose that we wanted to find the inverse transform of the rational function s plus 7 over s squared plus 1. Now, when we see the denominator there, s squared plus 1, our mind should immediately go to the idea that the transforms of sines and cosines have denominators that look like s squared plus k squared. So this has a denominator like that we get when we transform sines and cosines of kt, where k would be just equal to 1. In other words, the sine and the cosine of 1t. This suggests that we might break up this fraction into two fractions. What if we write it as s over s squared plus 1 plus 7 over s squared plus 1? Splitting it up into two parts, algebraically, we now see that the Laplace transform of that sum will be the sum of the inverse Laplace transforms. But we know what the inverse Laplace transform of s over s squared plus 1 is. That's a cosine of t. And we know what the inverse transform of 1 over s squared plus 1 is. That's the sine of t. Since we have 7 over this, our second piece has an inverse transform of 7 times the sine of t to give us that numerator of 7 in the second fraction. So by splitting up our rational function into two pieces, we separate it out into a piece that inverse transforms into a cosine and a piece that inverse transforms into a sine. By using clever algebra, we can oftentimes find inverse transforms. If we wanted to find what the inverse transform of the rational function 4 over s squared plus 5s plus 6 was, well, we might realize that that rational function down there can be, that polynomial in the denominator of the rational function can be factored. S squared plus 5s plus 6 can be factored into s plus 2 times s plus 3. Because that's the case, because 4 over this quadratic is really 4 over s plus 2 times s plus 3, we remember that using partial fractions, we could rewrite this as some combination a over s plus 2 plus b over s plus 3 for constants a and b. A little bit of algebra will then go on to show what those constants are. They're 4 and negative 4. 4 over s squared plus 5s plus 6 is algebraically the same thing as 4 over s plus 2 plus minus 4 over s plus 3. Having broken down the rational function into the partial fractions like this, we can now take the inverse transforms of each of these two pieces. When I see s plus 2 in the denominator, I realize that that is an expression that's going to come from the transform of an exponential, and specifically e to the minus 2t. When I see s plus 3 in the denominator, again, that comes from the transform of an exponential, specifically e to the minus 3t. So in the end, the Laplace transform of this rational function is the sum of the Laplace transform of these fractions. And their inverse transforms are 4 over e to the minus 2t and minus 4 times e to the minus 3t. So our solution in the end is that that rational function inverse transforms into 4e to the minus 2t minus 4 times e to the minus 3t. And there we have it, several interesting examples of inverse Laplace transforms. We'll continue to pursue this theory and take a look at the practice of finding inverse Laplace transforms in the next video.